this lecture of the linear differential equation. Today I am going to solve those linear differential equations which are reducible to the linear differential equation with constant coefficient. And in this series we have two linear differential equations. One is Cauchy homogeneous linear differential equation and another is the Legendre linear differential equation. So Cauchy homogeneous linear differential equation. Cauchy homogeneous linear differential equation. The differential equation A naught, say x power n into dny upon dxn plus a1 x power n minus 1 dn minus 1 of y upon dxn minus 1 plus a2 x power n minus 2 dn minus 2 y of dxn minus 2 plus a and y equal to some function of x. Here you can see that each term has degree n. Here each term has degree equal. This term has degree n, this term has degree n minus 1, this degree has degree n minus 2, and this is your an into y. So that means now here our coefficients are not constant. Here we have x power n as a variable, here we have x power n minus 1 as variable, and here we have the multiplier as x power n minus 2. So now our aim is to reduce these variables, and after reducing these variables, this differential equation will reduce into the linear differential equation with constant coefficient. Now if we denote d by dx as capital D, then this will be your a naught x power n d power n, a1 x power n minus 1 d power n minus 1, then a2 x power n minus 2 dn minus 2, then we will have the last term as an x power n minus n, that is x power 0, d power n minus n, that is 0. So we will have an of y equal to some function of rs, some function of x. So now let us reduce these variables. For that, let us change this independent variable into another variable, say z, by this substitution. So we have assumed that x equal to e power z, where z is another independent variable and z will be your log x. Now your d by dx, or here your d is, here we have already denoted that our d is d by x. Now dy by dx means your dy. This will be your, we can write it as dy by dz into dz by dx, and from here your dz by dx will be 1 upon x. So we will have 1 upon x into dy by dx. So from here, this is your dy by dz. So from here, therefore, dy by dx equal to 1 upon x into dy by dz. Or you can say that dy by dz equal to x into dy by dx. Or we can have the value of this operator dy by dz as x into dy by dx. And dy by dx was our d. So we can say that, so from here we can say that the value of x into d is d by dz. If we denote d by dz as some another variable rounded d, then please note that here rounded is the differentiation with respect to the independent variable z. So here your x d will be rounded d. This is your value of x into d. Again, let us differentiate this equation number 1 with respect to x. Again by 1, if we differentiate it one more time with respect to x, then we will get dy by dx of 1 by x dy by dz, and this is equal to d by dz into 1 by x dy by dz into dz by dx. Now dz by dx is 1 by x. Our dz by dx was 1 by x. Before doing this, let us differentiate this bracket. Now the differentiation of 1 by x will be minus 1 upon x square. Then we will have dy by dz, and the second term will be dy by dx of dy by dz. And we can write it as 1 upon x square dy by dz. And then this dy by dx can be written as dy by dz into dy by dz into dz by dx. Now dz by dx was 1 by x, so this is equal to 1 by x into d2 by dz2. So from here, if you multiply this whole equation by x square, then we will have x squared dy by dx2 equal to minus dy by dz into, in the right hand side we have x d2 by dz2. So we have this term. Okay. Now the value of d by dz is, x dy by dx. And we need the value of x squared d2 by dx2, and this is your minus dy by dz. And let me cross check the calculation. This will be your minus 1 upon x squared into dy by dz. Then we will have d by dx of 1 by, then we will have here 1 by x as a multiplier. There is a mistake. So we have already 1 by x. So this will be your 1 upon x squared. So here is no x. So if you remove your y, then we have the value of this operator as, say, d2 by dz2 minus dy by dz. And from here we can say that our x square d square is, this is your rounded d square minus d. So this means d to d minus 1. So therefore we can say that our x square d square is rounded d into d minus 1, where rounded d is differentiation with respect to z. Similarly, we will have x cube d cube as d into d minus 1, d minus 2, and so on. So, with the help of these formulae, x into d as rounded d, x square d square is rounded d into d minus 1, our homogeneous equation will reduce into the linear differential equation with constant coefficient. Now let us consider the Legender's linear differential equation. Legender's linear differential equation. In case of Legendre differential equation, now in place of x we will have some ax plus b into d power n. This is known as your this differential equation, say ax plus b power n dn I upon dxn plus a1 ax plus b power n minus 1 d power n minus 1 of y upon dx power n minus 1. Then the last term is a and y equal to rx. This is known as our Legendre linear differential equation. This is known as Legendre linear differential equation, and which is same as Cauchy linear differential equation, but in place of x now we have ax plus b. So let us assume, as in Cauchy linear differential equation we have assumed that x equal to e to power z. So here we will assume ax plus b as e to power z. So from here our z will be log ax plus b, and our dz upon dx will be your a upon ax plus b. So here you can see that we have a constant a here. So as in the Cauchy linear differential equation, with a similar calculation we will have this ax plus b into d upon dx. This will be your a time d by dz. This will be your a time d by dz, because in this case our coefficient of x is a, so we are getting a. And this can be proved very easily as we have done in the Cauchy linear differential equation. So we can say that a x plus b into d is equal to a into rounded d. And similarly, ax plus b whole square d square will be a square d into d minus 1. Ax plus b whole cube will be a cube d into d minus 1 d minus 2, and so on. So this is the value of these multiplier. And now with the help of these formulae, your Legendre linear differential equation will reduce into the linear differential equation with constant coefficient. Okay. Now let us solve few questions. Question number 1. Solve x squared d2y on dx2 plus x dy by dx plus y equal to sin x into log x into sin log x. Let us solve this question. So solution, this equation can be written as x square d square plus xd plus 1 of y equal to log x into sin log x. Let x equal to e for z, then your z will be log x and our xd will be your rounded d. Rounded d is the differentiation with respect to z, and your x square d square will be rounded d into d minus 1, where your d is d by dx. So we have changed the independent variable x into the independent variable z. So therefore this equation will become d into d minus 1 plus d plus 1 of y equal to, now your log x is z, so this will be your z into sin log x, that means sin z, because our log x is z. So from here we can see that we have d square minus d plus d will cancel, y equal to z into sin z. Now this is your linear differential equation with constant coefficient, and we know how to solve this linear differential equation. Your auxiliary equation will be m square plus 1 equal to 0. So our root will be m equal to plus minus I. So our complementary function will be c1 cos z, because we have changed our independent variable x into z. So this will be your c1 cos z plus c2 sin z. Now z is log x, so we will have c1 cos log x plus c2 sin log x. So this is our complementary function. We can write it as yc. Then particular integral. So our yp, that means the particular integral, will be equal to b square plus 1 of z sin z. Replace our sin z as the imaginary part of each for iz. So we can see that our sin z is the imaginary part of each for iz. So this will be your imaginary part of 1 upon d square plus 1, then z into e for iz. So now you can use the formula. If you take e for iz outside, then our d will be replaced by d plus I. So we will have d plus I whole square plus 1 of z. So this is equal to imaginary part of e for iz. Then this is your a square plus b square plus 2ab. So b square means I square is minus 1. So this plus 1 will get cancelled. So we will have d square plus 2id. And then z. Now we will use the binomial expansion. For that, let us take 2id common. Now in the bracket we will have d square 1 plus d upon 2i. as we have taken d common, so we will get 1 plus d upon 2i. Now 1 upon I means minus I. Now if you use the binomial extension, then we will get 1 minus d upon 2i and then the higher powers. As we know that the double derivative of z is 0, so all the remaining terms will get vanished. So we have, so this is equal to imaginary part of e to power ij into 1 upon 2 id. Then here we will have, if you take this z in the bracket, so we will get z, and d of z means derivative of z is 1, and 1 upon I means minus I, so we will get this term. Again 1 upon d stands for the integration, so integration of z will be z square by 2, then we will have ij upon 2. So this is equal to imaginary part of e to power ij. Then let us take this I in the bracket, so this will be minus ij square by 4. Then this I will cancel with this one, so we will get z by 4. Here the integration of z will be z square by 2, and we will have z by 4. This term is here. So now e to power ij is cos z plus I sin z, and then in the bracket we will have ij power ij square by 4 plus z by 4. So as we need only imaginary part, so our solution will be I times this term, so we will get z upon 4 sin z. Then the second imaginary part will be, when we multiply this term by this term, we will get minus z square by 4 cos z. So this is the particular integral of 1 upon d square plus 1 into z into sin z. As our z is log x, so we will get log x upon 4 into sin log x minus log x whole square by 4 into cos log x. So your final solution will be the sum of the complementary function plus the particular function. So their sum is the general solution of the problem. Let us solve few more questions. Question solve x square d2y dx2 plus 3x dy by dx plus y equal to 1 upon 1 minus e power 1 minus x whole square. Solution. This problem can be written as x square d square plus 3xd plus 1 of y equal to 1 upon 1 minus x whole square. Let x equal to e for z, then your z will be log x. So we have x dh rounded d and x square d square as d into d minus 1. Therefore, d into d minus 1 plus 3 xd is d, so d plus 1 y equal to 1 upon x is e for z, so we will get this term. So from here we will have d square plus 2d plus 1 y equal to 1 upon 1 minus e for z whole square. So now this is your linear differential equation with constant coefficient. Your auxiliary equation will be, 1 m square plus 2m plus 1 equal to 0. So we have two roots. This is your m plus 1 whole square. So we will have m equal to minus 1. So your complementary function, that means say yc is equal to c1 plus c2x. Now we will not take x because we have already changed our independent variable x into z. So this will be a c1 plus c2z e to power z. Now your z is log x, so we will get c1 plus c2 log x e to power minus z, and now e to power z is x, so we will get 1 upon x. So we can say that our complementary function is, therefore our complementary function is c1 upon x plus c2 log x upon x. This is our complementary function. Now let us find out the particular integral. So pi, say this is your yp equal to 1 upon, this is your d plus 1 whole square of 1 minus e to power z whole square. Here you can see that we do not have any direct formula to solve this one. So let us use the general method. For that, because we have the formula 1 from d minus alpha of fx is equal to e to power alpha x, then e to power minus alpha x, fx dx. So now if you use this formula, then this is equal to 1 from d plus 1 of this term can be written as, here your alpha is minus 1. If your alpha is minus 1, then this will be your e to power minus z. Then in the bracket, as our alpha is minus 1, so we will get e to power z upon 1 minus e to power z whole square dz. So we have this term. Now, if we take this 1 minus e to power z as t, then we will get, if we take 1 minus e to power z as t, then we will get e to power z dz equal to minus dt. So this is basically minus dt upon t square, and integration of 1 upon t square is minus 1 upon t. So this is your minus. So now I can use this formula. So with the help of this formula, we will get e to power alpha is our minus 1, so we will get e to power minus z, then again e to power minus z, and then here we will get e to power z. Now we have this bracket as e to power minus z upon 1 minus e to power z into dz. So you can see that this is equal to, now this term will get cancelled, so we will have e to power minus z upon integration of 1 upon 1 minus e to power z dz. Now let us take e to power z common, then we will get e to power, in the numerator we will get e to power minus z, and here we will get e to power minus z minus 1 dz. Now if we take e to power minus z minus 1 as t, then we will get e to power minus z as e to power minus z into dz as dt with negative sign. So this will be your e to power minus z into log e to power minus z minus 1. Okay. Now our e to power minus z was x, so this will be your 1 upon x log 1 upon x minus 1. So that means our particular integral is, therefore our yp will be minus 1 upon x log 1 minus x upon x. So your final solution will be the sum of the complementary function plus the particular integral. Solve 2x minus 1 whole square d2y by dx2 minus plus 2x minus 1 dy by dx minus 2y equal to 8x square minus 2x plus 3. Let us solve this question. So solution, we can also write this equation as 2x minus 1 whole square d square plus 2x minus 1 d minus 2 of y equal to 8x square minus 2x plus 3. This is your Legendre linear differential equation. Let 2x minus 1 into d is equal to, we let 2x minus 1 equal to e to power z, then your z will be log 2x minus 1, and from here the value of x will be e to power z plus 1 upon 2. And we know that 2x minus 1 into d is equal to 2 times rounded d, where rounded d will be the differentiation with respect to z. And similarly 2x minus 1 whole square d square will be 2 square into d minus 1. So on putting this value here, we will get 4 into d minus 1 plus 2 times d minus 2 of y equal to 8x square. X square means e to power z plus 1 upon 2 whole square minus 2 e power z plus 1.2 plus 3. So this is equal to 4d square. This 4d minus 4d plus 2d will be minus 2d minus 2 of y equal to 8. Now this will be a 4 to the 8. So we will have a square plus b square plus 2 times e power z minus e power z minus 1 plus 3. So therefore now you can take this to common or we have 4d square minus 2d plus 2 of y equal to, this is our 2 times e power 2z plus this is our 4 times e power z minus e power z, that is 3 e power z. Then we will have plus 2 plus 3 5 minus 1, that is plus 4. The question is I think this is minus 2. So auxiliary equation will be 4m square minus 2m minus 2 equal to 0. So from here we will have 2m square minus m minus 1 equal to 0. So we can write it as 2m square minus 2m plus m minus 1 equal to 0. So we will have 2m into m minus 1 plus 1 into m minus 1 equal to 0. So our m will be 1 or minus half. So your complementary function will be c1 e to power z plus c2 e to power minus half z. E to power z was, our e to power z was 2x minus 1. So this is your 2x minus 1 plus c2 e to power z was 2x minus 1 or minus half. So you can say that this is your c1 2x minus 1 plus c2 upon the square root of 2x minus 1. So this is the complementary function. Now let us find out the particular integral. For the particular integral, your particular integral means yp will be 1 upon 4d square minus 2d minus 2, 4d square minus 2d minus 2 of 2 e to power 2z plus 4d square minus 2d minus 2 of 3 e to power z plus 4d square minus 2d minus 2 of 4. 4 can be written as 4 into e to power 0z. Now if we replace d by a is 2, then this will be your 4 into 4 16. D is 2, so this will be your 4 minus 2, that means 6. So that means if you replace our d by 2, then this will be your 16 minus 4, that means 12 minus 2, that means 10. So this will be your 2 upon 10, that means 1.5 e to power 2z. Then here, on replacing d by 1, we will get, here you can see that, if you replace your d by 1, then we will get 4 minus 2 minus 2, that means 0. So in the numerator, we will have z divided by the differentiation with respect to z. So with respect to d, this will be your 8d minus 2 of 3 e to power z. And for the last term, let us replace d by 0, so we get minus 2 here. So this will be your minus 2 into e to power 0, e to power 0 is 1. So this is your 1 by 5 e to power 2z. Now let us replace d by a is 1. So this will be your 8 minus 2, that means 6, and 3 upon 6 means 0 upon 2 e to power z minus 2. As our 5, as our e to power z was 2x minus 1, so this is your 2x minus 1 whole square plus 1 by 2. Z was log 2x minus 1 and e to power z was 2x minus 1 minus 2. So our final solution will be the sum of complementary function plus the particular integral. So this is the solution.